This ECE 201 lesson is titled Current Division and Voltage Division. We plan to derive general expressions for current division and voltage division, and we also plan to do some simple examples seeing their use. They are part of a general approach to circuit analysis that involves circuit simplification and circuit reduction, which is a very useful approach to circuit solving that also, I would say, gives us some intuitive instinct into how circuits work. Let's first consider current division among parallel resistors. Here we see an arbitrary number of resistors, say n resistors, all in parallel with each other, also in parallel with the current source. Each resistor offers a branch of the circuit through which current may flow. So how will the current divide among these branches? Our goal now is to develop an equation to simply determine the current through any one of these resistors. To derive that equation, we're going to go back to the basics of circuit analysis, that is, connection constraints and element constraints. By Kirchhoff's current law applied, let's say, to the top node, I sub s will be equal to I1 plus I2 plus I3, etc., until we've accounted for all the branches. By Ohm's law, each resistor current is equal to the voltage across the resistor divided by the resistor value. And because all the resistors are in parallel, they all have the same voltage. That results from Kirchhoff's voltage law. So V1 equals V2 equals V3. Let's call that common voltage V. So I sub s is equal to V over R1 plus V over R2 until we've accounted for all the branches. Let's factor out that common term, that is the voltage V, and then divide the equation through both sides by the sum of all the reciprocal resistors. Now we have an expression for the voltage V. It's equal to the source current divided by the sum of the reciprocal resistors. So with this expression for voltage in hand, how does one get the current through a given resistor, say R1? Well, by Ohm's law, I equals V over R, so I1 is equal to V over R1. So the current through R1 is equal to IS times, in the numerator, 1 over R1, and the denominator, the sum of all the reciprocal resistors. And since 1 over R is equal to a conductance, we can say that I1 is equal to IS times an expression where the numerator is G1 and the denominator is simply the sum of all the branch conductances. More generally, considering the current through resistor J among n resistors in parallel, that current is equal to I sub s, the source current, times the quantity G sub J over the sum of the conductances, or equivalently the source current times the quantity 1 over R sub J divided by the sum of the reciprocal resistors. And this is our current division equation that we'll be making use of. And now let's turn our attention to the other topic of today, voltage division. Say we have a series of resistors, n resistors in series, and that they are also in series with a voltage source, V sub s. Can we also determine an equation that will allow us to state the voltage across, let's say, the jth resistor? Let's start again with the basics. By Kirchhoff's current law, the current through R1, that is I1, is equal to the current through R2, I2. R1 and R2 are in series. They share a node to which no other current carrying element is connected. And we see that R2 is in series with R3, so I2 is equal to I3. We know that if element 1 is in series with element 2 and element 2 is in series with element 3, then element 3 and element 1 are also in series. I3 is equal to I1. Well, all the resistors are in series here, so all the resistor currents are the same. Let's call that common current I. By Kirchhoff's voltage law, Vs is equal to the sum of the resistor voltage drops. And by Ohm's law, each individual resistor's voltage is obtained from Ohm's law, V equals I times R. And as we've noted, all the resistor currents are the same, the common current I. If we factor out that I, then we can simply say that Vs is equal to I times the sum of all the resistors. So the current I is Vs divided by the sum of all the resistors. Well, we wanted to develop an expression for the voltage across any given one of the resistors, say Rn. By Ohm's law, Vn is equal to I times Rn. We have the expression for I, so Vn is equal to Vs times, in the numerator, Rn, and in the denominator, the sum of all the resistors. This is a general expression for voltage division. Having derived the equations for current division and voltage division, let's put them to use in some simple examples. Let's start with current division. Let's say that we want to know the current through resistor R2. Well, by the general equation, we can say that I2 is equal to Is times 1 over R2 divided by 1 over R1 plus 1 over R2. Now, frequently people like to write this a little differently. Let's multiply the top and bottom by R1 times R2. In the numerator, we will just have R1, and in the denominator, we will have R1 plus R2. So another way to write this expression is to say that I2 is equal to Is times R1 over R1 plus R2. This expression just allows us to avoid taking the reciprocals, maybe saving a few strokes on the calculator. I want to point out, though, one heads up. Maybe somewhat counterintuitive. Note that what we're finding is the current through R2, but look what's in the numerator here. It's R1. So be careful in using this other form. This alternate approach is only useful where we have just two resistors in parallel. If we have three resistors in parallel, let's add another resistor here. Then we have to go back to the more fundamental approach, where we say that I2 is equal to Is times 1 over R2 divided by 1 over R1 plus 1 over R2 plus 1 over R3. So this handy little equation written on the bottom of the screen only comes into play when we have just the two resistors in parallel, which is nevertheless a fairly frequently encountered situation. And we must emphasize that the current division equation only applies when the resistors are in parallel. If we want to look at a three resistor network where they are not all in parallel, such as, for example, in this circuit where now we have R1, R2, and R3, but R2 and R3 are in series, not in parallel, I would no longer be able to use this expression. I could combine R2, R3 in series, make them an equivalent resistor, and then find use the current division equation to find the current through that branch. But we must remember that the general current division expression is for resistors in parallel. Well, now let's turn our attention to the voltage division equation that we derived. Let's say we have a source, V sub S, two resistors, R1 and R2. And let's say we desire to find the voltage across V2. This would now simply be equal to Vs times R2 over R1 plus R2. It looks like that one form of the current division expression. Here, though, we do have consistency with the resistor number and with the numerator resistors R2 in both cases. If we had more resistors in series, the denominator would have all the resistors added up. Whereas with current division, we had to make really sure that all the resistors were in parallel. Here, if we're going to use the voltage division equation, they must all be in series. Suppose, for example, we have another resistor attached to this circuit. And we want to know what's the voltage across R2. This is no longer true. And the reason it's no longer true is that R1 and R2 are no longer in series. The node that R1 and R2 shared also has R3 connected to it, a very important pitfall to avoid in applying voltage division. Let's pause a moment and just think about where we are in the big picture of solving circuits and circuit analysis. Early on, we know there was a method of writing down all the KCL, KVL, and element constraints. We have two terminal elements, capital E of them. We get two E equations for two E unknowns. What we've just talked about, though, is pointing to another basic approach. So another approach is to simplify the circuit using equivalent resistance contacts, source transformations, etc., to the point where we can solve for the circuit parameter of interest simply by using things like current division, voltage division, and Ohm's law. In this circuit topology, which actually we've seen in a couple of previous lessons, suppose we decide to solve for the current through I3, but we'd like to use some sort of a current division approach. How can we go about this? Let's put some numbers on the circuit. That has now been done in red. We have a 6-volt source, a 1 ohm resistor, and then a couple of fairly small resistors in parallel, a 3rd ohm resistor and a 1/2 ohm resistor. Current division requires all the resistors be in parallel, and that we have a current source also in parallel. We don't have that here, but suppose we make a source transformation with this 6-volt source and this 1 ohm resistance. That can be written as a 6/1 or 6 amp source in parallel with a 1 ohm resistor. Let me draw that in. Here the circuit is redrawn after that source transformation, and you can see that from the rest of the circuit's point of view, which includes the current I3 that we want to solve for, everything will be equivalent. So how will we go about this? Use current division. Here's our current division expression, 6 amps times 2/6, or 1/3 of 6 amps, or 2 amps. So here we have solved the circuit by simplification and by using current division. Earlier we talked about a pitfall with voltage division that we wanted to avoid. Here I'd like to show you another pitfall to avoid. Suppose that we had instead wanted to find the current through the resistor R1. Can I say, oh, the current through this resistor R1 is 1/6 of 6 amps or 1 amp? I'm going to put a big question mark beside that. This is the part of the circuit that was transformed. Its currents and voltages will have changed. The circuit was equivalent only from the rest of the circuit's point of view. Let's go back to the original circuit. So here's the original circuit again. The current I1 will be given by 6 volts divided by R1 plus the parallel combination of R2 and R3, and that is not equal to 1 amp. So when we do equivalent circuits and so forth, the part of the circuit that we are changing, we are changing. We don't expect the currents and voltages to remain the same there. But the rest of the circuit is in the sense where there is an equivalent circuit. Well, this concludes our ECE 201 lesson on current division and voltage division. We've derived the general expressions for current division and voltage division, starting from, not surprisingly, KCL, KVL, and element constraints. We've applied those general equations to a couple of examples. We've also seen some ways not to use those equations, some pitfalls that one could fall into. And we see these in the context of an analysis approach that involves circuit reduction or circuit simplification to focus on the particular variables of interest.